How's it going, everyone? In terms of the video content for this class, myself, like everyone else, I'm sure, doesn't like watching long videos. So rather than record a very long lecture, I'll try to break all of the videos up into 5 to 15-minute chunks. At the beginning, we'll kind of introduce the concept in general, and at the end, we'll do an actual example problem. And as we progress throughout the course, the example problems will take a lot longer of the actual video than the introductory material. Before we get started, I know that this class, once we get about a week or two in, is going to feel a lot like a physics or math class. But fundamentally, we're all engineers or want to be engineers, so I kind of want to keep an engineering perspective in mind before we start. In order to do that, we kind of have to agree on a definition of what an engineer is. And people's opinion may vary, but I kind of think of it as someone that has the capability to take scientific and mathematical principles and actually translate those to value in kind of the public domain or in the real world, you may say. So what I'd like you to do, have already registered for this class, so you probably have a basic idea of what statics is. So think about the material that we're actually going to be learning in this class. How do engineers actually use it on a day-to-day basis? So if you want, you can actually take and pause the video for like 10 to 15 seconds and kind of reflect on that concept. I'm guessing that the majority of you, when you thought about the application of statics in the real world, thought about applications in the civil domain, or things like large-scale structures, homes, bridges, skyscrapers, things like that. And maybe they come to mind because most fundamentally, they're the things that we rely on to not move. And as we'll see in a little bit later in this learning module, that's what statics is the subset of mechanics that deals with objects that don't accelerate at all. So I'm guessing the majority of you thought in that space, but maybe some of you thought on a smaller scale, kind of instrumentation or setups that may go inside a factory or a house, maybe the table in front of you that your computer is sitting on or the chair that you're sitting on. Hopefully it won't move. Maybe even less of you actually thought about kind of statics applied at a smaller scale to things like nanomaterial design or microelectrical machines or MEMS. Maybe you've heard of that. The key point that I wanted to emphasize by bringing up all of those different application domains is that statics really has applicability across a broad level of domains, right? You can apply it at various physical scales for things that are very large or things that are very small, and you can apply it across a bunch of different kind of engineering disciplines. It's not just a mechanical thing. It also applies for electrical and computer engineers as well, and of course, people working in the biomedical space that are dealing with biomechanics. In terms of what the customer or your coworkers are actually going to ask you to do with this material, these questions are often going to come out as worded as, hey, this thing that we've built, whatever it may be, the structure or this body, is it going to move under this particular loading condition, or is it going to break under this loading condition? So that's what I'm kind of referring to, excuse me, as an analysis question. And a lot of engineers, very often in your engineering career, you'll be doing that kind of work, right? If you're the mechanical engineer that has the statics background, you're going to be the guy that people take, or the guy or the girl that people take that question to. In addition, statics, of course, has applicability from a design point of view, right? Someone has a use case, they have certain requirements and specifications. They want you, in the case of statics, to choose the physical dimensions and the materials of the object to satisfy the constraints and fulfill the objectives. Key point that I want to emphasize, I'll use the term modeling, and that is kind of useful in both analysis and design type applications, where you're just trying to get enough of the physics and math on paper in order to be able to answer the question that you want. And I say on paper in this class because that's predominantly what we're going to be dealing with. Of course, in the majority of mechanical or general engineering design now, you're talking about actually capturing descriptions of structures in a computer-aided environment and actually kind of simulating the underlying physics using numerical methods. But that's many, many semesters down the road if any of you want to go that route. So let's get started with kind of identifying some basic definitions, and this is going to feel a lot like your physics class. I know a lot of you are taking physics 2 or dealing with electrodynamics, so this is going to be going way back for many of you. So mechanics is the study of motion, or the lack thereof, of bodies of interest, bodies in quotation, because this applies at a lot of different scales. We kind of need a generic word to describe the things that we're interested in, describing their motion or their lack of motion. So the way that we can kind of further subdivide mechanics is according to the way that these bodies react when forces are applied. So most fundamentally, If we think about maybe the table around us, it's subject to a lot of forces. As we'll see later in the lecture, it has mass, so it's attracted to the Earth. That force is called its weight, of course. We have these various support structures that are serving to keep it off the ground. So this table is subjected to a lot of forces. But if I kind of removed the effect of all those structures, those forces rather, the table would kind of look the same. So that's a case of what we'll call a rigid body or rigid body mechanics, because whether or not it's subjected to forces, right, the physical dimensions of it really don't change. Of course, we can have other types of structures such that when a force is applied, those physical dimensions change. There's actually a little bit of a deformation. That's called deformable body mechanics. And I'm sure that the majority of you that are on the mechanical engineering pathway are familiar with the idea of fluid mechanics. When you have a material that has that shearing force definition of being a fluid, right, it has its kind of own dedicated study of mechanics. We're going to start with rigid body mechanics because those are our learning objectives. I'm just joking. The reason that we're starting with rigid body mechanics is to be good at the other subsets. You need the fundamental concepts of rigid body mechanics. In addition, one thing that I wanted to kind of focus on is when we're talking about rigid body mechanics, and I'll update that bullet in the slide before I post these. We can further segment that into two subfields of interest. And I already alluded to this earlier. If the body is not subject to a resultant force, which is to say that it's not accelerating, as we'll get to when we get to the point of Newton's laws, we'll say that that's called statics if we're analyzing that kind of body. So key point being, the majority of time, it's going to be that it's not moving, but statics also considers a scenario where you have an object moving at constant velocity. Dynamics will just be all of those cases where the body is subject to acceleration. So why do you consider the two things separately? Well, it's related to kind of market applicability, right? There's lots of scenarios where you're dealing with structures that aren't supposed to move. So it's kind of worth its own field of study to understand statics. And of course, any material that we learn here will be very valuable wherever you choose to move on to dynamics at. Wanted to give you a little bit of a historical perspective. I know you all can read this in the text, so I don't want to hit on it in too much detail. But one thing that I want to say is oftentimes when you look at kind of the timeline or the chronological kind of progression of engineering, what usually happens from an engineering point of view, right, is there's some fundamental mathematical or scientific development that engineers kind of take advantage of and translate. So a lot of these developments that I'm going to call here, your textbook calls them developments in statics, but really they're kind of developments from the scientific point of view. Both science and engineering, it's an empirical discipline, right? We need data. And in order to have data, you have to be able to measure stuff. Well, when you think about kind of the fundamental quantities that describe static analysis, they're really easy to measure. So a lot of this stuff is really, really old. So the actual field of study of statics dates back over 2,500 years to the time period of about 287 BC, where you have Archimedes' lever, where he's describing a lot of empirical phenomenon from statics, kind of just using a primitive tool of a lever. But the majority of the stuff that you're probably more familiar with on the mechanics side is the work of Galileo in the kind of mid-1500s, and then, of course, Isaac Newton in the mid-1600s. We'll look a lot at his work in the next learning module. And the reason being that you have kind of that big jump in the progression of development between statics and kind of the dynamic phenomenon is in order to deal with dynamics. Previously on the previous slide, we said that it deals with bodies that are under acceleration. Recall back from your calculus that acceleration is just the time rate of change of velocity, which is the time rate of change of position. What word am I using often in there? Time, right? So in order to be able to really empirically study this stuff, you have to have a capacity to measure time at a relatively high resolution. So that the kind of lack of instrumentation or measurement equipment kind of explains that latency between the development in statics and dynamics. And if you notice, they're separated by about 1,800 years. That's not the only thing. I mean, of course, there's use case scenarios that are kind of governing that time separation as well. Moving on in fundamental concepts, there's 4 physical quantities that we're going to deal with in this class. The first is length, and length is going to be really important. Thinking back to that first slide where I talked about what statics really is, we want to be able to talk about the physical dimensions of things, along with the separation of bodies from one another. And to do that, we need some notion of length. In addition, when we get to dynamics eventually, which we won't in this class, but in the next class of mechanics, we'll need to have a notion of time. Of course, we need to have some notion of mass, as we'll see when we get into Newton's law, right? It's just a measure of how much physical stuff is inside a body, right? And as it's governed by Newton's law, that will determine for a given force how much the momentum of that object changes or how much it accelerates. Most fundamentally, the thing I want to focus in on this slide is we need to have some notion of what force means. So force is just a mechanical quantity that describes how two bodies can interact with one another. And fundamentally, two bodies can act with one another either in contact or at a distance. And the textbook describes a lot of these things in more detail. Of course, when you're talking about action at a distance type forces, you're talking about gravitational fields or some type of electrodynamic phenomenon. One thing that I want to bring up of the four quantities that we're dealing with in this class, the force is the only thing that, in order to unambiguously describe it or to describe it fully, we need to not only describe how much there is, i.e. its magnitude, but we also need to describe its direction. In addition, and you may, of course, recall, and we'll get to that a little bit later in this chapter, that anything that's described by a magnitude and direction is called a vector. But this particular vector, in order to completely kind of classify it, we also need to specify the point of application. And what that means is if I have any particular body, maybe like this pen, if I apply contact to it and apply a force, the resulting mechanics will be different whether or not the same force is applied here versus here versus here. And we'll see in a minute that's because in order to really model that, we're dealing with a rigid body instead of a particle. So perfect segue. So what does it mean to be a particle? Well, when you hear that from kind of maybe a chemical perspective, you think about it as something that's really, really, really small. But we're engineers, so we're interested in the math or science, but fundamentally we want to solve problems, and we want to solve the problems as quickly and cheaply as possible. So from a modeling point of view, we only want to include information into our models that's necessary to get the questions that we want answered. So we're going to call a particle anything that when we do a static analysis on, the physical dimensions don't matter, right? So it doesn't necessarily mean that sorry, my animations were a little bit off. That's kind of what I was hitting at the beginning there about the concept of minimalist modeling. But we're going to call anything a particle that we don't actually have to consider the physical dimensions of in our analysis. It doesn't mean that it's small. If we need to consider the physical dimensions, how big something is, in order to obtain our solution to the question of interest, we're going to call that a rigid body. Now, in order to be a rigid body, remember that it doesn't only mean that we're considering the physical dimensions of the object of interest, but also if forces are applied to that object, it also won't deform. So keep that in mind. Concentrated force, your book defines it. It's just basically the idea that even if you go back to when I had my hand under this pen, if I were to model that, which we'll see a little bit later on in the course, is done through a free body diagram, I'm going to kind of just assume that my finger rather is applying this force at a single infinitesimal point, one single point. But you can probably see that my finger is making contact over some broad area. So the idea of taking a force that's applied over some finite area and modeling it as a single vector applied at a single point, that's what they mean by a concentrated force. And maybe the simplest example of that we'll see when we get later on in the course is the idea of defining the weight of something. So clearly, when I think about myself, I'm made up of a distributed body consisting of my hands, my arms, all of these things. Each individually has weight, but I can describe my aggregate weight as a single force applied at my center of mass. And we're going to get to all of that later, but that's the key when your book is talking about a concentrated force. That's the idea that they're trying to convey. So let's wrap this up with an example, and I promise you the majority of the remaining of the lectures after we get out of chapter 1 will be like 70% example, 30% me just talking about concepts. So don't get discouraged if you just watch this and you're getting bored. But I took this image on the right from your textbook. They have kind of an old steel wheel railroad car on a track, and they've drawn in a white arrow here. So think about that image that the textbook authors are showing us, and particularly look at that white arrow that's representing the contact force that the rail is exerting on the wheel. So why are why is that force, or any force in general, drawn as an arrow? So take a minute and pause and kind of think back and make sure you remember why an arrow is such a good thing for representing a force. So hopefully you're back, and hopefully the thing that you realize is that an arrow, naturally when you draw it, it has a magnitude, which it has a length, right? When you think about drawing an arrow, you have to determine how long you want to draw it, and you have to determine in what direction you want to draw it. So naturally, it has two parameters, its length and its direction, that just so happen to align with the idea of a vector. A vector is generally defined by a magnitude and direction. And when you draw an arrow, you got to pick how long to draw it, and you got to pick in which direction to draw it. So forces are vectors. So vectors are naturally represented by arrows. So it's just a good fit. Two, assuming the wheel is made of steel, why would rigid body analysis assumptions likely be valid? Key point I'm trying to emphasize there is that this is a very strong material, so we can kind of assume that under normal weight loading within the actual car, this problem is kind of a loaded question. You kind of need to be able to think in advance a little bit more. But the key point being is when we think of steel, we think of things that are strong, that under most normal loading conditions aren't going to physically change their shape when we apply forces to them. So I hope that your first lecture module wasn't too painful. They're not all going to feel like this in general, and I went over my 15-minute mark. I am so sorry. I'll pick it up on learning module 2.